Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 9th, 2025. We're looking at an ICLR conference paper, Learning Randomized Algorithms with Transformers, published about 3.5 months ago. This paper explores teaching deep learning models, specifically transformers, which are advanced AI systems great at handling sequences to learn randomized algorithms. These are just methods that make some choices randomly. The idea is to make models more robust against adversarial inputs, those tricky inputs designed to fool AI. Because standard training, like expected risk minimization or ERM, which aims to reduce average error, doesn't inherently encourage this. Okay, so this figure on page 2 really clarifies their method. Part A shows the transformer taking in data plus a random seed. That's their random seed encoding. Then, part B is key. Models trained with standard expected risk minimization are either right or wrong, shown by those red bars. But they're models, trained with a special LQ objective, a training rule that encourages using that seed, show a spread of success in blue. And when they use majority voting, essentially getting multiple answers with different seeds and picking the most common one, performance in green really improves. Part C shows this random majority approach stays successful even on harder tasks. Alright, so to see how their special LQ training rule helps models use those random seeds, these next plots are key. The left graph shows predictive variance, how much answers change for the same input with different seeds, against that Q value. For low Q, common in standard training, there's little change, but as Q increases, especially past a, quote, phase transition around 16, the model's outputs really start to vary. The right-hand histogram confirms this. Low Q gives all or nothing success, but higher Q values show a spread, proving the model has learned to randomize its approach effectively. So building on how that LQ objective helps the model use randomness, this next figure, on page 7, shows it in action with graph coloring, which is like assigning colors to points in a network, so no connected points share a color. Part A shows the setup, a ring of points or vertices, where each only sees its immediate neighbors. Part B then shows a transformer, designed to also focus locally, using a random seed to decide the color for each vertex. And Part C really highlights the benefit. With different seeds, the model tries different colorings, making it much harder for an adversary to consistently make it fail. Let's move on to the next part regarding learning randomized algorithms. Okay, so this next figure, on page 8, shows the transformer tackling exploration in a grid world that's like a simple game map where it searches for treasure. Part A is the map. Part B shows the transformer using its seed to decide moves. Part C is key. Different seeds lead to different exploration paths. We see an initial exploration phase. Then it heads straight for the treasure. This unpredictability, driven by the seed, helps it avoid consistently poor outcomes or high regret, especially against an adversary trying to trick it. Okay, so now let's look at how this pans out for the graph coloring task we talked about earlier. These plots here really break down the performance. Part A shows success percentage against that Q value from their LQ objective. You can see the green line, representing their model using majority voting, where it takes multiple tries with different seeds and picks the most common answer, achieves near perfect success. Part B shows the loss, basically how much error the model makes. And Part C, the histogram, confirms that with a higher Q, like Q equals 10, the model shows a range of success rates, not just an all or nothing outcome. This varied success is exactly what they want for effective randomization. Alright, so now let's turn our attention to how this randomization plays out in the grid world exploration task we touched on earlier. These next plots really dig into the performance. Part A shows their randomized model. In blue, getting a better accumulated reward, that's its total score, and handling tricky adversarial inputs much better than a standard model. Part B then highlights that using enough random seeds during training, about 10 or more, is key. Finally, Part C shows their model explores the grid much more uniformly, learning diverse paths, unlike a standard model which tends to follow the same predictable route. So to wrap things up, we've seen how this approach allows transformers which are powerful AI models, to truly learn randomized strategies. The key takeaway is that by training with a specific objective called the LQ objective, instead of just standard methods like expected risk minimization, which typically doesn't encourage using randomness, these models can leverage random seeds to become much more robust, especially against tricky adversarial situations. And techniques like majority voting can then push their performance even higher. It's a fascinating step in making AI more adaptable. Thanks for tuning in to the AI Research Roundup. I'm Alex, and I'll catch you next time.